Till now we have seen that it is possible to construct a finite automata to accept regular language, but it is not possible to construct a finite automata to accept non-regular language. So what is regular language? We say that a language is regular if it is finite. Okay, so when the language is finite, it is always possible to construct a finite automata for that. So if a finite language, it will be regular, and when the language is regular, we can construct finite automata. And finite automata we have seen DFA, NFA and null NFA. Okay, now we say that if the language is infinite, okay, so when the language has to be accessed, and then there should be a loop inside the finite automata, right? Means there should be some kind of pattern. If there is no pattern in the finite automata, then finite automata is not possible. For example, if I say a language is infinite, and these are my states of finite automata, some q0, q1, and suppose q2, and then q3. Suppose this is the final state. So here we are saying there is a pattern. What is this pattern? Or some kind of loop from q1 to q2, and then from q2 to q1 there is a transition. So this loop, this is a loop, or we can say this is a pattern. So when the language is infinite, there should be always a loop or a pattern. Then only I can construct a finite automata for that. So when a language is infinite, there has to be some loop or some pattern, then only I can construct finite automata. So this is a finite automata, right? If I don't find any such pattern, then there is no finite automata for the language. So two things you have to remember: when the language is finite, there is it is always possible to construct finite automata. Finite automata, three types: DFA, NFA or null NFA. And the language is called as regular language. Okay, and if the language is infinite, there has to be some pattern or some loop, then only it is possible to construct a finite automata. Now for example, if we say a power n, okay, where n is greater than or equal to 1, okay, so the meaning is my language is minimum 1a is possible, because n is greater than or equal to 1. And when n is greater than 1, so 2a or 3a or any number of a is possible. So if I have to construct a finite automata, so this is also infinite, but their machine need not remember anything. Okay, so suppose if I say there are two states, q0 and q1. Q1 is a final state, and then at least one a should be accepted. So the minimum string is a, and then more than one a, any number of a is fine. So we'll put self loop. So this is the finite automata, and here machine need not remember anything. Now if I say, basically why we say we can't construct a finite automata for infinite language: if there is some pattern or loop, machine need not remember anything. Finite automata does not have it cannot remember infinite length string. That's why we can't construct a finite automata for infinite language. And if there is some loop or pattern, machine need not remember anything. That's why we can construct few cases. Okay, now if I say a power n, b power m, where n and m greater than and equal to 1. So here you can see a power n means and both are greater than and equal to 1. So minimum 1a and 1b should be accepted. So 1a and then 1b should be accepted. Okay, so and then more than 1a or more than 1b, will put self loop. So this minimum length string for this, it will be a, b, or a, right, b. The meaning is any number of a and any number of b. And here also, since it is infinite, but machine is not remembering anything, because n and b are independent of each other. So any number of a and here any number of b, right? Now if I say we have a power n, b power n, and then n is less than and equal to, suppose, something like this. So here also n is bounded. Okay, it is bounded. So the language is infinite. So language is, sorry, it is finite, not infinite, because it is bounded, so it is finite. So whenever we say it is finite, it is possible to construct finite automata for this. Now if I say we have a power n, b power n, where n is greater than and equal to 1. So see here, n is bounded here, and here it is not bounded here. See, basically what we are saying here, a power n, b power n, and n is greater than and equal to 1. So the meaning is my language should contain all the string which has same number of a followed by same number of b. So n is greater than and equal to 1. That means ab, or if there are 2 a's, there should be 2 b's. There are 3 a's, there should be 3 b's. If there are 4 a's, there should be 4 b's. So machine has to remember number of a for number of b's. So if suppose if I say I have 100 a's, so I cannot have 99 b's. So machine has to remember the number of a's. So machine cannot remember infinite length string. So that's why, because it can count only finite length string. So that's why it is not possible to construct finite automata for this. So this is not a regular. So this is non-regular. This is non-regular. Right? Now if I say we have WWR, okay, and where mod of W is equal to 2 and W belongs to A, B star. So the meaning is W is a string which is made up of A and B. So W has, means a string has any combination of, string is made up of any number of A and B. So it's a combination of A and B basically. And WWR if I say, so for example, and here we are saying the mod of W is equal to 2. Okay, so now the language will be, the language for this will be, what all string will be there? If the W is AA, WWR will also be AA. If the W is AB, the WWR will be reverse of that, BA. So if it is BA, it will be AB W, and if W is BB, WR will also be BB. So this is W and this is WR. So here language is finite, so it is regular and it is possible to construct finite automata for this. Now if I say WWR and W belongs to AB star, so there is no such condition like mod of W is equal to 2. So here any combination of A and B can come. So if I say my language, if it W is ABA, WR should also be ABA. If I say I have 100, if I have 1 2 3 4 5 6 A and 6 3 4 5 6 B, so WWR will be, it will be, WWR will be what? It will be 6B and then 6 A's. So here machine has to remember W for WR. Okay, so then in this case it is not possible to construct a finite automata. So finite automata does not have capacity to save infinite length string. That's why finite automata cannot be constructed for this particular language. Okay, so this is also a non-regular, this is also a non-regular language. Okay, now if I say I have a power n, b power m, c power k, and n, m and k greater than and equal to 1. So here there is nothing to be counted or nothing to be remembered. Why? Because a power n, b power m, c power k. So n, m and k are independent of each other. So there is nothing to be counted or nothing to be remembered. So we can generate A independently, then B and then C. So here it is possible to construct a finite automata for that. Right. So we say that we can construct finite automata to accept a regular language, but it is not possible to construct finite automata to accept non-regular language. So for regular language, we have finite automata, and for finite automata, we have regular grammar. Okay, and I have already discussed in my previous video what is acceptor and what is generator. So acceptor is nothing but the machine. Here in case of regular language it will be finite automata, and generator means which will generate the entire language, so that is called as the grammar. So for regular language the grammar is regular grammar and the machine is finite automata. Now we say that for some languages we cannot construct finite automata, so that is called as non-regular language. So if the language is non-regular, so there has to be some machine for that, that is called as PDA, or we also call it push down automata, and the grammar for that is called as context free grammar, and the language is called as context free language. Okay, so when it is non-regular we call it context free language, and machine for and for context, see, like regular language we construct finite automata, machine is finite automata. So for non-regular language, what machine is push down automata and the grammar is context free grammar. Okay, so next video lecture I will discuss how to write a context free grammar. Okay, and then after that we will discuss how to construct a push down automata. Okay, so hope the concept is clear to you. Thank you for watching.